In this example problem, we're going to solve for the temperature profile of a cylindrical wall or a pipe. So in this problem, a cylindrical wall carries a hot fluid which creates an elevated temperature at its inner wall. So that would be here. The outer wall loses heat to the ambient, causing its surface temperature, Ts2, which is located at R equals R2, to be cooler than that of the inner wall, assuming temperature variation only in the R direction and with the constant surface temperatures shown as boundary conditions. Solve for the steady state temperature profile, TR. And we are also going to solve for flux as a function of R and the total rate of heat as a function of R. And these are both in the R direction. Okay, so let's look at this problem. So this is called a cylindrical wall. It's just a pipe wall, but as you can see, it's a cylindrical system. But basically, in a cylindrical wall, we're only concerned about what's happening in this region, from this inner radius to the outer radius, denoted by R1 and R2, respectively. So how do we go about solving this problem? We want to solve for a temperature profile, so we are going to use the heat diffusion equation, or the heat equation. If you recall, an energy balance can be very useful in helping you to solve for temperatures, and the heat equation is just an energy balance, except that it's an energy balance done on a differential scale, so it covers energy balance and the change in energy over space and time. So by solving it, we'll actually get our temperature profile over space and time. Except in this particular case, we are looking at a steady state problem. So when we look at the heat equation in cylindrical coordinates, we do not have this accumulation term. Temperature is not changing with time in this particular problem. We are not told anything about generation, so we can get rid of that. So we want to look at these change in temperature with respect to our spatial coordinates. So this term represents the change in temperature with respect to a change in this angle, and that angle would be basically this direction. So that would be the angle phi. So this problem has a natural symmetry. We're expecting this fluid on the inside to be well mixed, and we're expecting the fluid on the outside to also be well mixed. So we expect everything that's happening to be symmetrical with respect to this center point here. So we would not expect any temperature gradients in the phi direction. So we can get rid of that term. R is the distance from the center here of our coordinate system. So R would be going out in this direction. How far are we from the center? Because we have this hot fluid and a colder ambient, we will expect temperature gradients in the R direction. So we'll need to keep this term. Z would represent the axial direction. That would be down the length of the pipe. So in and out of the screen would be the Z direction, and we don't expect any temperature variations in the Z direction for this particular problem. So we're only looking for our temperature profile as a function of R. And as I mentioned, in addition to flux and total rate of heat flowing in the R direction. So we have successfully reduced this equation to just an ordinary differential equation. We no longer need to use the partials because temperature is only varying with respect to one other variable, which is R. K is going to be a constant. We have a constant thermal conductivity. So K we can pull out of here, and we end up with an equation that looks like this. K over R times the derivative with respect to R of this quantity, R dt dr. So R itself here is not a constant, so we cannot just pull it out algebraically. R by nature is something that changes as you go from 0 here at the center out to that outer radius. So R is definitely not a constant, so we cannot pull it out of that outer derivative. And that whole quantity on the left equals 0. Okay, so how do we deal with this second order differential equation? We want to separate and integrate. We can do that on this particular problem. So what you see here, assuming R, we're only going to be considering R going from within this wall. So only R's between R1 and R2 is what we'll consider. So R will be a non-zero term. It'll be a finite positive number. K, thermal conductivity, is also always a positive number. So here we have a positive number multiplied by this other quantity, and this positive number multiplied by this other quantity has to equal 0. So this other quantity has to be 0. If you take a positive number and multiply it by something that equals 0, then that something has to be 0. So what that allows us to do is it allows us to divide both sides by this quantity k over r. So when we divide that out, it sort of just disappears, but we're able to do that, to justify that mathematically, because we know that any finite number multiplied by 0 equals 0. So we know that this quantity has to be 0. So that reduces our equation even further. So we're left with this, and it's stating that the derivative of this quantity r times dt dr equals 0. So it doesn't say that the second derivative is 0 like in the plane wall system. So we wouldn't necessarily expect our temperature profile to be this straight line, and we'll just do the math and see how this works out. So let's begin to separate and integrate. So we would multiply both sides by dr, the differential change in radius. We would then integrate both sides, so we get r times dt dr is equal to, the integral of 0 is just 0, but we do pick up a constant of integration as we integrate. Okay, so now let's rearrange and do this again. If we multiplied both sides by the quantity dr over r, then we successfully move r and the differential r over to the right hand side and keep dt on the left hand side. So then we can integrate again, and we end up with temperature equals, so the integral of dr over r, as you probably know, is the natural log of r. So we get c1 times natural log of r, and then we pick up a second constant of integration. And I've done this, I did not apply, we don't have a flux boundary condition, so I went ahead and integrated until we got into temperature form. Both of our boundary conditions are surface temperature, so we want to integrate until we get all the way to temperature before applying boundary conditions. And because this was originally a second order differential equation with respect to r, that means we're going to need two different boundary conditions, and that's confirmed by the fact that we have these two unknown constants. So let's first apply our, let's look at our boundary conditions. So we have, when we're just going to assume that these are known temperatures, that TS1 and TS2. So we have at R equals R1, we have T is equal to TS1. So let's go ahead and, well, let's look at the other boundary condition as well. At R equals R2, we have T equals TS2. So when we substitute those in, so we'll take our generic form of the equation and we'll substitute in these boundary conditions to each equation to give us two more specific equations that we can solve for our two unknown constants. So after doing that substitution, we get TS1 is equal to C1 times the natural log of R plus, oh, that's R1 plus C2. The second one gives us a very similar equation. TS2 equals C1 times the natural log of R2 plus C2. So we have two equations that look very similar, except the only difference is that you have TS1 and R1 in the first equation, TS2 and R2 in the second equation. So what we could actually do to help eliminate some variables is we could take this first equation and completely subtract off the second equation. So we subtract off TS2 from the left-hand side and this quantity C1 natural log of R2 plus C2 from the right-hand side. So that would give us a different form of the equation, which would also be true. So we get TS1 minus TS2 is equal to C1. I'm going to use the distributive property here and pull out that C1. And there is another property of natural logs that tell us that the natural log of R1 minus the natural log of R2 is equal to the natural log of R1 divided by R2. So our equation takes on this form. So if we solve this part for C1, we get that C1 is equal to TS1 minus TS2 over the natural log of R1 over R2. Okay, so it can be easy to get lost in the math, but just remember we started with an equation that makes physical sense. We could actually go back and derive the heat equation from Fourier's law, which we did for Cartesian coordinates. So it's easy to get lost in the math, but just stick with it. Just get proficient at doing these integrations, and then after you get something useful from here, then you can go back and analyze this from a conceptual point of view. Okay, so now if we go back to, we know what C1 is, we've solved for it completely. Let's go back to this equation. So we know what C1 is now. Let's go back and solve for C2. So if we solve that equation for C2, we end up getting C2 is equal to TS2 minus C1 times the natural log of R2. And I am just leaving this as C1 for now, just to save myself some writing. So going back and substituting everything back in, we go back to this general form of our equation here and plug in both C1 and C2. So let's do that. So we end up with our temperature profile. Our temperature as a function of R is equal to, here's our C1, that's TS1 minus TS2 divided by the natural log of R1 over R2 multiplied by natural log of R, which is just this part. Then we need to add in C2, so that's going to be plus TS2 minus, now we have C1, which is TS1 minus TS2 divided by natural log of R1 over R2, and then this is going to be multiplied by the natural log of R2. So it's starting to look a little bit more manageable. You can see these very similar terms here, so we can go ahead and combine those terms. So we're going to get, if we simplify this equation a little bit, we get TR equals TS2 plus, we're going to take this C1 here, which is TS1 minus TS2 over ln R1 over R2, and then that is going to be multiplied now by the natural log of R over R2. And that is our final equation in this simplified form. So that is our temperature profile. So when you are given these particular circumstances, steady state, a cylindrical wall with constant surface temperature boundary conditions, no generation, and a constant thermal conductivity, this is how your temperature profile ends up looking. So it's a function of R, as you can see, so your temperature is going to change as a function of R, and specifically it has a natural log in there, which is a nonlinear term. So we will expect to see temperature change in a nonlinear fashion with respect to R. If you have different types of boundary conditions, for example, a no-flux boundary condition where the one surface may be assumed to be perfectly insulated, or if you have a convection boundary condition or a constant flux boundary condition, the form of this equation would change because your constants of integration would change. So you'd have to just resolve the equation and to get that. This general form, this solution would still hold, but the algebra would work out to be different. Okay, so the other part of the question that we were trying to answer was, so we know our temperature profile, and I'll plot that for you here in a minute so you can visualize it. The other part of our question was, how does flux look as a function of R? So flux is minus K dt dr. Flux in the R direction is minus K dt dr. So first, we would go back and differentiate our temperature profile that we just derived. So dt dr, in this case, we know that, so the derivative of TS2 with respect to R is just 0. The derivative of a natural log is going to be 1 over R, so it's just the derivative of a natural log, so 1 over R multiplied by this pre-multiplication term. So that derivative is just Ts1 minus Ts2 divided by R times the natural log of R1 over R2. So then our flux ends up being, we just take that whole thing, multiply it by minus K, so I want to have you observe something about this equation. Everything in this equation is a constant except for R. So what we're going to expect, because R is going to be increasing as you go from the inner radius to the outer radius, so as R increases, then your flux is going to decrease. As R gets bigger, your flux gets smaller and smaller. And that is because as you go out further and further away, there's more and more area. As R gets bigger, there's more and more area normal to the flow of heat, so that if you have a constant amount of heat, then that heat is being dissipated over an increasing surface area as you go out further. So if we wanted to get Q in the R direction as a function of R, then we would take our flux and multiply that by the appropriate area. So the appropriate area would be 2 times pi times R, which is the perimeter around a circle, and then we would multiply this by the length of the pipe. So multiplying that through, we get, or rather substituting this for Q, we get 2 pi RL multiplied by Ts1 minus Ts2 divided by, oh, and we need a minus K in there still, divided by R natural log of R1 over R2. So you probably noticed that there are some simplifications that we can make, specifically that this R is going to cancel out. So if you examine this equation and you look at the flow of heat as a function of R under these particular circumstances, you'll notice that every single term is a constant. So our total rate of heat is a constant. So let's go look at some graphs. I've taken the liberty of just taking each of these equations and plotting them in Python. So I had to come up with some values for all these constants. So using all these different values, this is how temperature looks. So this is a natural log function. So we see this higher temperature here at the inner radius of 0.1 meter, and then it comes down. You can see that it does go through our boundary conditions. So that's something you always want to check is, do your boundary conditions apply? If not, well, are your boundary conditions valid? If not, you've done something wrong. So yes, at R equals 0.1, we see that our temperature is 200, and at R equals 0.5, we see that our temperature is indeed 50 degrees C. Okay, so let's look at flux. Remember, the flux was proportional to 1 over R. So we see that you have a much higher flux at this inner radius, and then the flux gradually gets smaller and smaller. That heat is dissipating as it's going out radially. That flow of heat is encountering more and more area normal to the flow of heat, so that term, that energy in terms of watts, is encountering a bigger and bigger area, so it gets smaller and smaller. And then if we look at the flow of heat as you go out radially, that is just totally constant. So basically, if you think about it this way, here is our pipe. If we have a certain amount of heat that's going to come out, that heat is going to get from within our inner fluid out to this outer fluid, and it's going to be losing heat in all directions, but if you measured the total amount of heat as a function of R, it's going to be constant. So if we took a snapshot and if we integrated the flux at any particular point as a function of R, we integrated the flux all around that surface area, we'd find that the value of that integrated flux, also known as the total rate of heat, is the same. And if we did that here or here, and assuming our system stays nice and symmetrical, that flow of heat is the same all the way out to here even. It's just the heat gets less and less concentrated. So even though the flow of heat as you go out radially stays the same, the flux decreases because it's it's getting dissipated the further out you go from the center of your cylindrical system.